We hear all the time about the incredible decisions artificial intelligence can make, but how often do we really stop and ask why it makes them? Well, in this explainer, we're going to unlock that black box and see exactly what the AI sees. So let's get right into it.
Right, let's imagine a really high-stakes situation. An AI analyzes a chest X-ray and flags it for pneumonia. Now, that diagnosis could literally save a life. But here's the catch. Its reasoning is a complete mystery. We have the answer, but we have absolutely no idea how it got there. So, is the AI focusing its attention here on the actual lung tissue, what doctors call the parenchyma, the place where the signs of an infection would actually appear? If it is, then great. We can start to trust it as a valuable clinical tool, a sort of digital partner for radiologists. But what if it isn't? What if it's actually looking at something completely irrelevant, like, say, the hospital's watermark tucked away in the corner of the image? Well, if that's the case, its prediction isn't just a bit off, it's dangerously, fundamentally flawed. To solve this mystery, we first need to take a peek inside the AI's mind, so to speak. The AIs we're talking about are called convolutional neural networks, or CNNs for short, and they have a really unique way of seeing an image. Understanding that process is absolutely key. You see, a CNN builds its understanding layer by layer. The very first layers see only the most basic things, simple lines, corners, maybe a change in color. Then, the middle layers start to combine those simple shapes into more complex textures and patterns. It's only in the final deep layers that the network really starts to recognize high-level ideas, like an eye on a face, a wheel on a car, or the shape of a tumor.
Now, here's what's really clever. Throughout this entire process, the network creates something called feature maps. Think of them as grids that keep track of where each feature was found. So even when the AI is thinking about a really abstract concept like cat, it hasn't forgotten where it saw the whiskers or the pointy ears in the original picture. This spatial memory, well, that's the crucial piece of our puzzle.
And the clue that lets us finally peer inside lies in a very specific bit of the network's design, right near the end, a special layer known as global average pooling.
In older networks, you'd take all of those rich, detailed feature maps and just flatten them. Squash them all into one enormous long list of numbers. And just like that, all that precious where information was completely lost. The new way, global average pooling, is so much more elegant. Instead of flattening, it just compresses each map down to a single number, its average value. So this one simple step gives us this neat little summary of everything the AI found in the image. But more importantly, it provides a direct link between those high-level features it saw and the final decision it made. It gives us the weights we need to figure out which features mattered the most.
Okay, so with those weights, we've got everything we need. We can now actually build a visual map of the AI's attention, and this is what we call a class activation map, or CAM. The process itself is surprisingly straightforward. First, you take those final feature maps. Second, you multiply each map by how important it was for the final decision. Those are the weights we were just talking about. Third, you add all of those weighted maps together into one single master map. And finally, you just resize it and lay it right over the original image.
And the result is brilliant. When it works perfectly, you can really see it. For an AI trained to find dogs, the heat map literally glows warmest over the parts of the image that scream dog. The face, the ears, the snout. It shows us plain as day that the AI is looking in all the right places.
Now, in a medical setting, the implications are just profound. A heat map for a tumor classifier absolutely must light up over the suspicious area on the scan. This allows a human expert to verify that the model didn't just get the right answer, but that it got it for the right reasons, based on the correct evidence.
But this exact same tool can also reveal when something has gone terribly wrong. What happens when the AI is getting the right answers, but for all the wrong reasons? And this is where we get to the real twist. An AI can have almost perfect accuracy on its test data and still be completely useless in the real world. A class activation map exposes this exact problem. The AI gets the answer right, but it's looking in completely the wrong place.
So the heat map might reveal something pretty shocking. The model isn't learning medicine at all. It's not identifying diseases in the lung tissue. No, it's cheating. It's learned to connect the disease with something else, like a text label a technician put on the X-ray, or maybe a mark left by a specific scanner.
And this is the danger, right? AI is brilliant at finding patterns, but it has zero common sense. It learns these shortcuts, these spurious correlations, linking a hospital watermark to a disease. A model that looks brilliant in the lab would be dangerously unreliable if you took it to a new hospital. And just looking at the accuracy score would never, ever tell you about this fatal flaw. This exact problem, the need for explanation, not just accuracy, drove the evolution of this technique. The goal became to make sure we could demand this kind of accountability from pretty much any model, not just the ones with that one specific design.
You see, the original CAM technique needed that specific global averaging pooling layer to work. But a more flexible successor came along called GradCamp. It generalized the whole idea. Instead of needing one type of layer, it uses something called gradients to figure out how much each part of the image influenced the decision. And this clever change means it can create a heat map for almost any CNN out there, which makes this kind of explanation way more universal.
And this really brings us to the most important point of all. In high-stakes fields like medicine, accuracy by itself isn't enough. In fact, it can be dangerous if we don't know why the model is accurate. And on the flip side, an explanation for a model that doesn't work well is just insufficient. You have to have both.
Ultimately, tools like CAM and GradCam are about so much more than just debugging code. They're about building trust. They are fundamental tools for creating a future where we can actually understand and hold accountable the complex AI that we rely on more and more every single day.